Hi everyone, this video is about isomorphic graphs. I think rather than define it first, I'm going to show you what I mean by isomorphic. So I've got two graphs here, and they don't appear to be the same, right? One of them's got this horizontal line, one of them's got this vertical line. But if I were to arrange these points, right? So this sort of arranging is allowed in graph theory. If I just move those points around, right, and connect them in that same way, I can get this graph to look like this graph here. So what I've just shown here is that this graph is isomorphic. And if you are able to move the two graphs around in order them to get them looking similar, then you've proven that they're isomorphic. But I want to show you a little bit more formal of a way to figure out if you have two isomorphic graphs. And that's going to be using these things called adjacency matrices. So an adjacency matrix is going to be this matrix or a table of all these connections, so we can show that these two graphs are isomorphic when we have something that's a little bit more complicated than just 4 vertices. So I've already started drawing one here, but I've got a graph with some labeled vertices here. So this is if you'll remember the vocabulary from the last time, this is a pseudograph, right? Because we have vertex 1 connected to itself. And this also happens to be a multigraph. So a multigraph has, if you look at vertex 1 and 3, you've got 2 edges connecting along there. Okay, so this adjacency matrix is going to let us know that graphs are isomorphic to each other, because if graphs are isomorphic, then we can draw their adjacency matrices. They'll have the same adjacency matrix. So I'm going to start filling this one in. Notice I've made a table here of vertex 1 through 5 on top, since I've got 5 of them, and also on the columns. So just to start filling this in, if you notice, there's no connection between vertex 4 and vertex 1. So there's no connection between vertex 1 and vertex 4. So V1, V4, that entry is going to be a 0. And it's also actually mirrored along this diagonal here. So V1, V4, we can see that connection is also 0. All right, so you'll start to see the mirroring a little bit more. Vertex 1 is connected to vertex 1 by 1 edge. So I'm going to write a 1 here, but that is the only pseudograph, right? 2 is not connected to itself, 3 is not connected to itself, 4 is not connected to itself, 5 is not connected to itself. So we can write zeros along this diagonal here. Let's see, vertex 1 and 2 are not connected, so we can write zeros here and here. Vertex 1 and vertex 3 do have not just one connection, but they actually have 2 connections. So vertex 1 to 3, vertex 1 to 3, we've got a multigraph, so we can write a 2 here and a 2 here. I'll start going a little bit quicker now that we've got the idea. So 2 and 3 are connected by 1 edge, so that'll be a 1 and a 1 there. 4 and 5 are connected by 1 edge. 3 and 4 are connected by 1 edge. 2 and 5 are not connected. 2 and 4 are connected. 1 and 5 are also connected. And let's see, 3 and 5 are not connected. So this is a table we can use, but the adjacency matrix is just a little bit more compact of a form for this. We assume that once we've labeled our vertices 1, 2, 3, 4, and 5, that once we've done that labeling, that they're going to be in this order and they're going to look like this. So our adjacency matrix is just going to be one big parentheses, and then I'll write out these same numbers that I've got in the table. Okay, so this thing is called our adjacency matrix. Right. So this is our adjacency matrix for this graph here. Right. Once we've made an adjacency matrix, again, our definition that we can use to figure out if something is a isomorphic graph or not is we can say that adjacency matrix, or graphs that we can draw graphs that we can draw That's what I'm looking to say here. So graphs we can draw such that they have the same adjacency matrix are isomorphic. And again, just like before, this can here is important. This can here is an important aspect of it. Like I said, the can, right, very important. Right. Graphs that we can draw such that the have the same adjacency matrix are isomorphic. So, for example, if I labeled these vertices as 1, 2, 3, 4, and I labeled these vertices as 2, 1, 3, 4. So changing this vertex here, we would have different adjacency matrices, but this can here implies that we can do this by labeling, right? So we can change the labels of these vertices such that they're isomorphic. All right. Okay, so that's how you make an adjacency matrix for a graph. If you want to prove that two graphs are, isomorphic to each other, you're going to have to do a little bit of experimentation. So here's an example of two graphs and we want to figure out if these graphs are isomorphic or not, right? So if I make a quick adjacency matrix for these two, we've got 5 points here. So I'll just start off with 1 to 1 is 0. I'm actually going to pause this. I'll draw these up and then resume it. Okay, so I've got these adjacency matrices written out, and what we can see from these two adjacency matrices is that they're not the same, right? So just to in this column, for example, 1 0 0 1 0. And we've got 1 1 0 1 0. So these two are not going to be the same. But that doesn't necessarily mean that these aren't isomorphic, right? It's possible that if we labeled this a different way, that we would get a adjacency matrix that was the same for both of these. So what we can try to do is start moving these around a little bit. So I'm just going to try and line this one up as best I can to match the numbers that I've got over here. So 3 goes down here, 5 goes up here, and 4 goes down here. So we can see that we've got something slightly off here, right? So these don't appear to be the same shape of graph with this current labeling, right? 1, 2, 3, 4, 5. But we can try to make this shape look like this other shape. So I'm just going to do some experimenting with this here. That's starting to look a little better. Oh, not quite. How about something like that? There we go. So now you can see, okay, if we arrange it like this, so if we change the labeling and made this one 1 and this one 5 and this one 2 and this one 3 and this one 4, then we do have an isomorphic graph. So that definition that we have for isomorphic, saying that they can have identical adjacency matrices, that's just a matter of labeling them, right? So I'll go ahead and see how much untangling it takes to get back to my original spot. There we go. All right. So yeah. Anyway, these are isomorphic, and we can show that just by moving these vertices around. So just because the adjacency matrices aren't equal doesn't mean that they're not isomorphic. Okay, so you just saw me move around some vertices to try and get this graph to look like this, and it's more than just experimentation. We can actually try some things out that'll make our lives a little easier. So the next problem I want to work with here is seeing if these, we can say, are these are these graphs isomorphic? So we'll do that in pen here. Let's say are. Are any of these graphs isomorphic with each other? And the answer to that, I'm actually going to take away the labels for these for a second. We can spend some time trying to rearrange these. And if we can rearrange them enough, then we might be able to get these of graphs to look like each other. So for example, I might be able to manipulate that. Oh, that kind of looks like this, so maybe moving it around this second graph here, starting to look a little bit more like this third graph, maybe not quite still. But anyway, we can try and do some experimentation with that. But something that we can do to help educate our guests is to talk about the valence and make a list of valences for each vertex in this graph. So I'm just going to use this convention for labeling 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just for now. And I can make a list of the valences for these. So what I mean by that is if I can just talk about the valence for each of these, if I can talk about the valence of each vertex. We can at least get some hints about whether or not these might be isomorphic graphs. So if I start with vertex 1, that's going to have a valence of 3. Vertex 2 is going to have a valence of 2. Vertex 3 has a valence of 3. Vertex 4 has a valence of 3, and vertex 5 has a valence of 3. So if I want to come up with this valence list here, I can simply write that as 3, 2, 3, 3, 3. Okay. So I'll do this next one a little bit quicker now that we understand what that what I mean by valence list. Here, let me see if I can move this over. Okay, so my valence list for this one is 3, 2, 3, 3, 3. This next one, valence for the first one is 4, 2 has 3, 3 has a valence of 4, 4 has a valence of 4, 5 has a valence of 3. And then valence list on this one, we've got, looks like 4, 2 has 4, 3 has 3, 4 has 4, and 5 has 3. Now, like I said, for isomorphic graphs, we know that the order doesn't matter, so I'm just going to go ahead and rewrite this valence list from smallest to largest. So I can reorder these numbers in this list. 2 and then 4 3s there. This one would become, let's see, 3 3 4 4 4. And this one would also be 3 3 4 4 4, right? Just arranging them from smallest to largest. What we can infer from this, right? We've got this valence list that's got 2 and a bunch of 3s, and this one has only 3s and 4s. So that means that this one on the left, graph A, let's call it, right? Graph A cannot be isomorphic with graph B, all right? But it's possible, at least, that graph B is isomorphic with graph C here, right? Now, I say that it can be, right? I'm not saying that if you come up with this valence list and that two graphs have the same valence, that means that you can say that they're isomorphic. That's not what I'm saying. I am only making the claim that if I call these A, B, and C, graph A, sorry, graph A cannot be graph A cannot be isomorphic to graph B, but graph A B can, let's maybe say might, be isomorphic to graph C. Okay. So when we say might, that's a big might there, right? So we want to see if we can we want to see if we can turn that might into a definitely. So I'm just going to do some moving, some copy pasting. Sorry. You know what? Okay, so that's graph B. That's graph C. So I can take advantage of the fact that I know that these have the same valences to try and move my points around. So I'm going to stay away from labels for just a second here and try to think about instead these two spots that have valences of 3. And I'm going to try and put those in the same spot and see if I can arrange everything else around those two. So here's my one vertex that's got a valence of 3, and here's my other vertex that's got a valence of 3. So I'm going to move my vertices around in that same position. Right, here's my vertex with a valency of 3. Here's got a valence of 3, and you can see just by moving that one piece around there, now I've got a set of two isomorphic graphs, right? So if I labeled these 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, they would have the same adjacency matrix. We could say they're isomorphic to each other. This kind of experimenting is good because you can get you can use the fact that you've got these valences. There are instances, however, I should warn you that if you have the same valence list, you might still not be able to recreate the same graph on there, right? Okay, so that's it for this section. There's going to be one more, and that'll be everything you need to know for quiz 7. All right, I'll see you in the next one.